Walk into a dark room and flick on 2 standard light bulbs. The space instantly fills with a smooth, perfectly even wash of light. It seems normal, but there is a direct conflict between what we see and the laws of wave physics. Agar light sach mein ek wave hai, if light is truly a continuous wave, then the waves from these 2 distinct bulbs should be crashing into each other. When wave peaks collide, they amplify. When a peak hits a trough, they cancel each other out. We should be seeing a literal zebra pattern projected on the living room walls, alternating stripes of intense brightness and pitch black darkness. Yet we never see those dark stripes. You can add 10 more bulbs to the room, and the light simply gets brighter and more uniform. The mechanics of wave optics are invisible in our everyday lives. To actually see those interference patterns, the light must follow a strict hidden condition known as coherent sources or kala sambandh. This equation describes why the bulbs fail to cleave a pattern. Final brightness depends on how the 2 waves overlap. This third component is the interference term. Here, the phase difference, angle phi, determines if the waves reinforce or cancel. Standard light bulbs are incoherent sources. Inside them, billions of individual atoms emit tiny bursts of light randomly and independently. Because of this chaos, the phase difference fluctuates millions of times every single second. Because of that rapid fluctuation, the value of cosine phi averages out to exactly 0 over time. That completely wipes out the interference term from our equation. Physically, this leaves us with only the simple addition of the 2 intensities. The potential for bright and dark stripes is erased, leaving behind nothing but uniform light. To force a stable interference pattern to appear, the phase difference must stay constant. Kalantar constant hona chahiye. The challenge is figuring out how to lock the microscopic random emissions of light into perfect sync. Coherent sources must be derived from a single parent source. The first method, division of wavefront, perfectly synchronizes distinct waves by splitting them through 2 narrow openings. The second method, division of amplitude, splits a wave through partial reflection, like on a soap bubble. By tricking a single beam into splitting, we bypass the chaos. Any random phase jitter from the parent source happens to both of the split beams at the exact same time, keeping their mathematical relationship locked. Now that we are using coherent sources, the phase difference stays locked, and the hidden zebra stripes of wave optics finally emerge. Bright fringes occur wherever the waves perfectly align. When cosine phi hits +1, the equation reaches absolute maximum intensity. The dark fringes occur when waves meet entirely out of sync. Cosine phi drops to -1, mathematically canceling into total darkness. If destructive interference causes light waves to perfectly cancel each other out to create black spots, is that light energy permanently destroyed? व्यतिकरण में ऊर्जा कभी नष्ट नहीं होती, बस उसका पुनर्वितरण होता है. In interference, energy is never lost, it is merely redistributed. Looking at the principle of conservation, we see that total energy remains constant. If you measure the average intensity across the entire striped pattern, the total amount of light is the same as before. The light missing from those pitch black bands hasn't vanished. It was mathematically pushed into the neighboring bright bands, making them twice as intensely bright as they would be through simple addition. The 2 bulbs in your living room blur this reality into a flat average brightness. But when light is brought into coherence, we see that the law of energy conservation is never broken. It simply organizes into a pattern,